So welcome to our fourth lecture, dealing with gas laws. In the previous lecture, we managed to come up with our four basic gas laws. Ahmed's law, that says the pressure of a gas in a container depends on its temperature. Boyle's law, that says the pressure of a gas depends on the volume of its container, but it's a reciprocal relationship. Charles' law, which says the volume, if the pressure is constant, depends on the temperature. And finally, Avogadro's principle that says the volume of the gas depends on how much gas you have. And so we can use these simple equations to answer questions about gases. For example, what is the pressure inside a gas piston with a volume of 10 liters if the pressure inside the piston was 2 atmospheres when the volume was 25 liters? Well, it's a pressure and volume problem. That makes it a Boyle's law problem. And Boyle's law says the pressure is equal to a constant times 1 over volume. Well, the reciprocal volume is sort of a pain. We can just multiply the whole equation by volume, and we get the original pressure times the original volume equals our constant. But that's also got to be true at the end. The final pressure times the final volume has to be equal to that constant. Well, if the original is equal to the constant and the latter is equal to the constant, then they must be equal to each other. And so we have the problem-solving form of Boyle's law. PV equals PV. So the original pressure was 2 atmospheres. The original volume was 25 liters. We don't know what the final pressure was, but the final volume was 10 liters. So get everything we know on one side, everything we don't know on the other side, and we find out that the pressure of the gas should now be 5 atmospheres. The volume went down, so the pressure had to go up. How about another problem? What is the pressure inside a gas cylinder at 25 degrees Celsius if the pressure was 755 torr when the temperature was 25 degrees Celsius? Well, this is pressure and temperature. That makes it an Ahmed's law problem. Pressure is a constant times temperature. Well, again, we want to isolate the constant, so we divide both sides by temperature. And we get the original pressure divided by the original temperature as our constant, and the final pressure divided by the final temperature has to be equal to that same constant, and so we have the problem-solving form of Ahmed's law. So 755 torr divided by the original temperature equals the final pressure divided by the 5 degrees Celsius, and the answer is 704 torr. The problem is if you do the math, that's absolutely not the answer you're going to get. So what's wrong? Well, is Ahmed's law wrong? Well, no. The temperature went down and the pressure went down, so Ahmed's law isn't wrong. So what is wrong? Why didn't we get the right answer? So what is wrong? Well, when we originally talked about Ahmed's law, we weren't talking temperature, we were talking energy. And that is where our problem is. If we're going to talk about zero energy, then that has to be where the temperature is 0. And that's not true for Celsius. At 0 degrees Celsius, things still have a lot of energy. If we're going to use temperature to represent energy, then 0 temperature has to equal 0 energy. And so we need to use an absolute temperature scale. In other words, we're going to have to use Kelvin. Anytime you're doing a gas problem, you have to use Kelvin. So back to our Ahmed's problem. The original pressure is 755 torr. The original temperature was 298 Kelvin. We don't know what the new pressure was going to be, but the new temperature was 278 Kelvin. And now we can solve for the pressure. Multiply both sides of our equation by 278, and we find out that the final pressure is indeed going to be 704 torr. And this is something you have to keep in mind. Anytime you are doing a gas problem, you have to use absolute temperature. That is, you have to use Kelvin. If you use Celsius or Fahrenheit, you are not going to get the right answer. Now we can rearrange our gas laws into their problem-solving form. Ahmed's law, the original pressure divided by the original temperature equals the final pressure divided by the final temperature, but those temperatures have to be Kelvin. Boyle's law says the original pressure times the original volume has to equal the final pressure times the final volume. Charles' law says the volume divided by temperature has to equal the new volume divided by the new temperature. And again, those have to be absolute temperatures. Any gas law problem that includes temperature has to be done in Kelvin. And finally, of course, Avogadro's principle that the volume divided by the amount of gas equals a new volume divided by a new amount of gas. And so we see that our gas has four variables: pressure, volume, the amount of gas, and temperature. The bad news is they're not independent variables. Ahmed's law says pressure and temperature are related. Boyle's law says pressure and volume are related. Avogadro's principle says volume and amount of gas is related. And Charles' law says volume and temperature are related. So they're all interrelated. We have four variables, but they're not independent variables. They all depend on each other. The problem is what if you change two of them? What if you change three of them? What if you change all four of them? What happens? And so we need something that includes more than just two of them at a time. So what can we do? Well, consider just Boyle's law. The pressure times the volume, original pressure times the volume equals the final pressure times the final volume. But Ahmed's law, we says that pressure is just a constant times temperature. And Avogadro's principle says that the volume is just a different constant times the amount of gas. And so we can replace pressure and volume in our equation with a constant times temperature and another constant times N. And what we end up with is PV equals a constant times temperature times the amount of gas. Well, a constant times a constant is just a constant. And so we can rewrite our equation as pressure times volume equals the amount of gas times R, our universal gas constant, times temperature. So now we have one equation, and it includes all four of our variables: pressure, volume, gas, and temperature. And all we need to make it work is R. And we have R. Well, actually, we have several R's. The problem with R is that it has to include the units for pressure, volume, moles, and Kelvin. And depending on what you use for pressure, since we have both atmospheres, torrs, and kilopascals, R has a different value. Well, actually, it doesn't have a different value. R is, in fact, a constant. It has the same value. But it has a numerically different value depending on what the units are. Like we said, if you measure how wide a room is using inches, feet, and meters, are you going to get the same answer? Well, yes, the room's the same size. No, you're not going to get the same number in inches, feet, and yards, but yes, you are going to get the same size. The size depends on what units you're using. The size of the room doesn't depend on the units. It's the size it is. What number you get depends on the units, but the size of the room doesn't change. And in the same way, R is a constant. But what its numerical value is depends on what units you are using in your problem. And so this is something to keep important in mind. Anytime you are using the universal gas law constant, you have to make sure that you have the right units on it. Otherwise, the numbers will give you the wrong answer. As we've said, one of the things that chemists spend their time doing is measuring the properties of matter, making measurements and doing comparisons. One of the things they like to measure, for example, is density. And for most solids and liquids, density tends to be a really good measurement of properties. It tends to be a characteristic of the material itself. That, of course, doesn't work for gases. And the reason, of course, it doesn't work for gases is because density is mass divided by volume. Well, what volume would a gas have? Well, that would depend on what volume you made available to it. The gas will occupy whatever volume you make available to it. So you can take the same amount of gas and get all sorts of different volumes for it, therefore all sorts of different densities. So if we're going to do a comparison of gases, we do in fact have to agree on what conditions we are talking about. Which brings us to STP, what is known as standard temperature and pressure for gases. So, standard temperature and pressure for gases, often abbreviated STP. Well, we got a pressure, 1 atmosphere. That's equal to 760.0 torr, equals 101.3 kilopascals. We need a temperature. Well, we got one. 0 degrees Celsius equals 273 Kelvin. Anytime you see a capital STP in a gas law problem, they're referring to standard temperature and pressure for gases. And so now we can start solving problems that involve more than just 2 of our variables. We can now start solving problems that involve all 4 of them. Well, yes and no. Why yes and no? Yes and no because they are in fact not independent variables. You can't change all 4 of them. Once you have picked 3 of them, you are stuck for the 4th one. And so we only can work with 3 of our variables, and then the last one we're forced to go with whatever the answer is. So let's consider a problem. So let's consider a problem like, what is the volume occupied by 1 mole of a gas at STP? Well, PV equals nRT. Divide both sides by P, and we get V equals nRT divided by P. So 1 mole of gas, our pressure is 1 atmosphere, the temperature at STP is 273 Kelvin, and we need an R, and you go back to look at the 3 R's I gave you. We have to find one that includes atmospheres and moles and Kelvin, and that is 0.08206 liter atmospheres moles Kelvin. And so that's the one we need to use. Do the calculation. The answer is 22.4. Moles cancel moles. Kelvin cancels Kelvin. Atmosphere cancels atmospheres. And we are left with units of liters. So 1 mole of gas at STP would occupy 22.4 liters in volume. And so we talk about the molar volume of a gas at STP. 1 mole of gas occupies 22.4 liters. And that brings us to the end of our discussion of gas laws for today. Have a nice day and see you at the next lecture.